Hello again, incoming pharmacy students. This is Brandon coming at you with the 5th installment in your Belmont Pharmacy Math Orientation. In the last video, we talked about dimensional analysis and how it was used and kind of unit conversion. We did a few examples, but I wanted to do another video just to run through a bunch more problems and talk about dimensional analysis in that kind of problem-solving setting. So without further ado, let's jump right into it. So, dimensional analysis problems. Obviously, one aspect in which we saw it in the last video was unit conversion. So we're going to just get back to speed with a couple unit conversion problems. So we're going to start out converting 80 ounces to kilograms. And remember, we can do this with that proportional equation stuff that we kind of did in that first and second video. But we learned last time how to also apply dimensional analysis to this kind of problem. So we're given that 2.2 pounds is equal to 1 kilogram. The problem is we are currently in ounces. So we first have to figure out how to get from ounces to pounds before we can finally arrive at our destination, which is kilograms. So we are starting out with our 80 ounces. That is what is given to us. And so then we multiply by that given rate created by the equivalency between these two fields, ounces and pounds. We know that there are going to be 16 ounces in 1 pound. So we know that 16 pounds and 1 ounces are going to go in this rate, and we have to know that we're going from ounces. So we need ounces to be on bottom so that that unit cancels out, right? So we've got 16 ounces on bottom, 1 pound on top. Now we have to take this transition from pounds into kilograms. And so we set up yet another rate, again with pounds and kilograms, using the equivalents we've got above. 2.2 pounds is equal to 1 kilogram. And here again, pounds is going to go on bottom. So that, again, the units will cancel out nicely. We want the one we want to cancel out to be on the opposite side of where it was before. So we're going to put 2.2 with the pounds on bottom and 1 with the kilogram on top. And then we just, multiply our tops, multiply our bottoms, and then go from there. So we've got 80 times 1 times 1, so that's just 80. And then we've got 16 times 2.2 on bottom, 35.2. And we're going to get 80 divided by 35.2 is around 2.27 kilograms approximately. And we know that we are in kilograms because all of our units canceled out. And the only unit that was left was in kilograms. That's an excellent check to always make sure that everything else is canceled out and you're in the unit that you want to end up with, in this case, kilograms. Let's do it again now with a volume of liquid rather than a weight. So here we're going to go from teaspoons to liters, and we're given the equivalents for teaspoons to milliliters. So again, we've kind of got this two-step transition, right? We got to go teaspoons to milliliters, and then we can go milliliters to liters. So we start out with our given, right? We're given our 10 teaspoons. That's our starting point. We need to go from teaspoons to milliliters. And notice we need teaspoons to cancel out. So in this first rate, we're going to need teaspoons on bottom and milliliters on top. We're given that equivalence as 1 teaspoon to 5 milliliters. So put the 1 with the teaspoons, put the 5 with the milliliters, and we notice that the teaspoons are now gone. We are now in the realm of milliliters, but that isn't where we want to end, right? We want to end in liters. So now we set up our next rate, milliliters to liters. And again, we want milliliters on bottom so that it can cancel with the milliliters that was previously on top. And from our third video, all about the metric system, we know that there are 1,000 milliliters in 1 liter, or, of course, You can say that there is 0.001 liters or 10 to the negative third liters in 1 milliliter. You can go at it either way, but that's how that would be set up. And so multiply tops, multiply bottoms. Notice we are in liters, so we have reached our destination, which is always good, always a good check. So we got 10 times 5, that's 50. 1 times 1, of course, is also still 50. And then 1 times 1,000 is 1,000. So 50 divided by 1,000, that is going to be 0.05 liters. So 10 teaspoons is the same as saying 0.05 liters. And we just did that by setting up our two rates in such a way that the units canceled out properly when we multiply. Okay, let's do another example with more complicated units. We did one that was like a miles per hour to minutes per second. We'll do one that's more in this kind of pharmaceutical context. So we have 2,000 milligrams of a drug is placed in 500 milliliters of NS and is ordered to be given at a rate of 10 milligrams per minute. We want to calculate this flow rate in milliliters per hour. So let's take stock of, what is kind of important in this problem. Here is our current flow rate, right? This is our starting. We're given a milligrams per minute. That's what we want for our patient to receive. Every minute, they need 10 milligrams. We want to convert this to milliliters per hour, presumably because, the drug is placed into a liquid solution. And so we are, infusing it, injecting it into them. And so we need to put it into that more volume liquid flow and figure out how fast we need that to flow every hour. So let's start there. So we have 10 milligrams per minute, which is really just 10 milligrams over 1 minute, right? Those are the same things. So notice we need milligrams to change to milliliters, and we need minutes to change to hours. So we have really two steps that are kind of going on here simultaneously. And you can cover these in either order, does not matter. So let's just start with the top. Let's start with changing milligrams to milliliters. So we need to figure out what is that relationship going to be? Well, it gives it to us, right? 2,000 milligrams is placed in 500 milliliters. So that's kind of the connection there. 500 milliliters of the solution is equal to 2,000 milligrams of the drug. So we're going to put that there, 2,500. And we need milligrams to cancel out. So milligrams is going to go on bottom and milliliters on top. So we have 2,000 with the milligrams is 500 milliliters, and the milligrams cancel out. And we are left with milliliters, which is what we want. So the top part is success. We are good there. So now we just need to, change the minutes to hours. So minutes is on bottom in this case. We know there are 60 minutes in 1 hour. So that's going to be the equivalent we use here. And here, minutes is going to go on top, right? Because it's found below before. So to cancel it out, we need to put it on the top side. And 60 minutes in 1 hour. So we put that in. And then we are good to go there. So we have 10 times 500 times 60 on top. That turns out to be 300,000 milliliters, if you want to keep that, over 2,000 hours. And if you divide those, you're going to have 150 milliliters per hour. And there we go. We have changed this rate of milligrams per minute to milliliters per hour, which will be more beneficial, more useful to us to figure out exactly how fast we need to inject this solution into our patient. And of course, dimensional analysis has a variety of uses. Really, any time you have stuff going on with units and you want to kind of change it and look at it from a different aspect, dimensional analysis is an excellent way to go because you have these equivalencies here and you can very visually see how to manipulate things so that they kind of cancel out. So you can use it in scaling and dosage and concentrations, all of these different uses for it. So I've got a few more examples that we're just kind of going to go through, a couple more complex ones, just kind of getting more practice with this dimensional analysis kind of concept. So next question, 30 units of a particular compound is injected 4 times daily. How many pens? We have 50 units per milliliter and 4 milliliters per pen will be needed for a 30-day supply. So again, got a lot of things going on here. So identify the most important ingredients here. We got 30 units. That's injected 4 times daily. And we know we need a 30-day supply. And then we've got these, different conversions to get from units to ultimately pens. Pens is our final unit that we want our answer to be in. So there's a couple different ways you can go about this. It all ultimately ends up being the same. It's just really how your mind kind of organizes the data and how it kind of works through this particular problem. So when I see this, I would think about trying to find the total number of units that you would need over that 30-day supply first, and then worry about converting from the units to the pens. That's where I would go next. So we have 30 units injected 4 times daily for 30 days. So we can kind of think of this as 30 units is 1 dose, right? So we can think of it that way. And there are 4 doses every day, right? And this is good because now our doses kind of cancel out. And we've got 30 days. Now, obviously, some of you might have just seen, 30 units times 4 times 30 gets us the total number of units. This would be how you would kind of think of it from that dimensional analysis perspective. Because notice, our final thing is all in units, so we're good there. So if we do that, 30 times 4 times 30, that's going to get us to 3,600 units in total for that 30 days. And now that we have that, we can extend it to go from units to pens. So this is our new starting point, is 3,600 units. We just need to convert this to pens, and we are given that it's 50 units per milliliter. We want the units to cancel, so we're going to put the units on bottom, milliliters on top. It is 50 units in every milliliter. And then we're still not done because currently our answer is in milliliters. We want it to be in pens. So now we need milliliters and pens. We've got that relationship there, 4 milliliters per pen. So we're going to put milliliters on bottom, so it again cancels. And 4 with the milliliters and 1 with the pen, obviously. And looky here, we are now in pens. Good check. So we are good in terms of our units, which is very important. So we have 3,600 on top, divided by 50 times 4 is 200, and that's going to give us, I believe, it's 18 pens. So given all of these conversions, a person would need 18 pens for that 30-day supply for this particular compound. And it would only cost them like $300,000. So it's okay, right? Just kidding. And there we go. It all came back to that kind of dimensional analysis kind of thing. We used it first to figure out the total number of units that we would need for that 30 days. And then we converted that to pens. You could have done this technically in one long equation. I like having it broken up so that I know this is where this 3,600 units kind of comes in. And I can use that as my benchmark, my baseline for the conversion to pens. That's just the way my mind thinks about it. Again, your mind might think through it differently. Honestly, a lot of the calculations will end up being the same. Let's do another problem. A loading dose of 3 grams is ordered for an antibiotic suspension. If the suspension is available in 200 milligrams per milliliter, how many milliliters are needed for the dose? So we basically have this rate for the suspension, is 200 milligrams per milliliter, and we need 3 grams. We basically are trying to convert this grams to milliliters in kind of a weird way. And so that's basically where we're going to go. We're going to go from this grams. We need that to be in milligrams to kind of work with that suspension, the 200 milligram per milliliter power of that suspension, in order to get to milliliters. So that's where we're going to go first. We're going to go from grams to milligrams and then use that in order to get to milliliters. So we start with 3 grams. Our first step is to go to milligrams. And again, based off our conversation about the metric system, we have grams and milligrams. We want grams on bottom, right? So the grams cancels out. And there are 1,000 milligrams in 1 gram, or again, 1 milligram is 0.001 grams. Either way, you can do it that way. So we're in milligrams. And then we need to basically convert it to the milliliters. And we know we have 200 milligrams found in every milliliter. We put the milligrams on bottom so that it cancels out, right, with the 1 before. And notice that we are, in fact, in milliliters, which is what the problem says that we need to be in. So we are good to go there. So we have 3 times 1,000 times 1, it's 3,000. Over 1 times 200 is 200. So that's going to be 15, and the unit is milliliters. And that just came from, we went from grams to milligrams, and then used the concentration, the amount of drug in a particular liquid, in order to get into that volume 15 milliliter kind of aspect. There we go. Simple as that. And let's do one last problem. So this one has a few more numbers, and it will turn out that some of this will be very extra kind of info here. So this will be good practice to kind of see what's going to be important, what's not going to be important. So let's read through this carefully. So a patient is prescribed an antibiotic for 12 milligrams per kilogram per dose thrice daily for 14 days. So right off the bat, we've got a patient. This antibiotic is prescribed per kilogram. So basically, it is a dosage based off of our patient's weight, and that's going to prescribe or tell us how much each dose is going to do. And notice that it's 3 times per day for 14 days. So we've got basically 3 different important numbers just in that first sentence alone. We've got the patient weighs 75 pounds and is 50 inches tall. And just be in their case file or whatever, just to kind of give us a little more background on the patient. Obviously, the pounds is going to be important because that's what the strength of our dosage is going to be based off of. The suspension is available in a strength of 60 milligrams per 5 milliliters. Again, we've got that drug and kind of that liquid suspension kind of thing. And is available in 50 milliliter and 100 milliliter bottles. Okay, so it comes in 2 different sizes of bottles. And our question, after all that, how many teaspoonfuls per day will the patient receive? So our final answer needs to be in teaspoonfuls. And we've got a few important rates that are kind of given there. So let's kind of work through this. So I like to start with the end. We look at the end question and figure out what are we actually looking for, because that will inform our decision about like what is important in the background info about. So we've got teaspoonfuls per day. So right off the bat, 14 days doesn't matter. We don't care about that. We're only concerned with how much happens each day. If it was over the entire 2-week span, then we would need to know that. But here, since it's just per day, that's not important. We also don't really care about the size of the bottles, right? Because we don't care about what the container is. We're just curious about the strength of it and how that relates to the antibiotic itself. And also, we notice in our first sentence, we've got this 12 milligrams per kilograms per dose. So the antibiotic strength is just based off their weight. So the height isn't going to be important here. Sometimes height will be important because other medicines might be based off of maybe a body's surface area or those kinds of things. In this case, it's just based off of their weight. So the 50 inches isn't as important here. And so now I think we've got it so that there is just the important info. The 12 milligrams per kilograms per dose, 3 times a day. The patient's 75 pounds. We've got the suspension. We want to go to teaspoons. And we've got those 2 rates at the end that are going to help us do that. Again, there's going to be a variety of ways that kind of get us to that same solution. But this is how my brain's going to kind of organize this info. So again, your brain might do it differently, but all the calculations will end up pretty much being very similar. My first thing, just like last time, where we figured out the total amount needed in that 30-day thing, I'm going to say, how much do we need per day? So I'm going to look at 12 milligrams per kilograms per dose thrice daily. And so really what this is saying, this is going to look very weird. We've got 12 milligrams per kilograms each dose, and it's for 3 doses. And so think about it with that kind of dimensional analysis aspect, the doses kind of cancels out. So it's just 12 times 3 tells us that we're going to need 36 milligrams per kilogram. And that might look weird having like this compound unit over unit kind of thing. But that's really what's going on here is you need 12 3 times. So 12 times 3 gives 36. It's another way to kind of look at it. So now we have the amount needed of the drug per kilogram of the patient. So that would probably be another place to start. Our current weight for our patient is in pounds. So we need to convert that to kilograms so that that kind of works with our strength of our drug, right, for our dosage. So we start out in 75 pounds. And we know that 1 kilogram is 2.2 pounds. So we want pounds to be on bottom, kilograms to be on top. There are 2.2 pounds per kilogram. And that's going to come out to be some long decimal, 34.09 repeated. I'm actually just going to leave it at 75 over 2.2. And I know that looks weird, but it's always good to kind of keep things as general as possible and not round too early. That's the thing I see a lot with students is they like to round as soon as possible. All that does is create error. And especially in a field like pharmacy, we want to mitigate as much error as humanly possible. So try to wait to round until the very last step, if possible. So we've got 75 over 2.2 kilograms as our weight for this patient. And so now we can start to kind of put things together. We can use these 2 pieces of fact, the 75 over 2.2 kilograms, with the 36 milligrams per kilograms to basically figure out the milligrams of drugs needed. Right, so we're gonna go over to the next slide because I knew we were gonna run out of room. So 75 over 2.2 kilograms. We want to go to milligrams. So we have 36 milligrams per kilogram. We want kilograms on bottom, milligrams on top, and it is 36 milligrams per kilogram, yes. And so the kilograms is going to kind of cancel out there. Note that, of course, the milligrams and the kilograms are 2 different things, right? The milligrams is the drug, the kilograms is the patient. So make sure to not try and do any wonky conversion there. They're measuring 2 different things. So even though they're the same, weight kind of thing, don't try to kind of combine them. And so there we go. We've got that. Now we're in milligrams. Our object, right, is to get to teaspoonfuls. So we need to get to milliliters first using the strength of our liquid suspension, 60 milligrams per 5 milliliters. So we've got milligrams on bottom and milliliters on top so that we are good. Now we're in milliliters. And we have one more conversion because remember our answer is in teaspoonfuls. And we're given that 1 teaspoon is 5 milliliters. So we need milliliters on bottom to cancel that out. And there are 5 milliliters in a teaspoon, right? Yes. And notice we have used all of those pieces of information that we deemed were important for these things. We didn't use the 14 days. We didn't use the size of the bottles. We didn't use the height. But everything else was useful and was used. And we are in teaspoons, which is a good sign. And so now we're good to go, right? So we just multiply tops, multiply bottoms, and we can just put the 2.2 on bottom. So that's going to be good there. So we have 75 times 36 times 5, 13,500 divided by 2.2 times 1 times 60 times 5, 660. And then we divide those two, and I make sure to put in the correct numbers. And we get around 20.45 teaspoons. 20.45 repeating. That is our final answer in amount of teaspoons per day that our patient will end up receiving. And so let's kind of look back, see how we kind of thought about this and how we used dimensional analysis to solve this. So first, we figured out how many basically milligrams or per kilograms, how much of the antibiotic we needed every day by multiplying by 3. That got us to 36. Since that was in kilograms, we had to convert our patient's weight to kilograms. We did that. And then we started combining them. So we used the kilograms, multiplied that by the milligrams per kilograms to convert it basically to milligrams to figure out how much milligrams per day would be needed. That was this one. Then we used the liquid strength or liquid, the strength of our suspension to convert that to milliliters to figure out how much milliliters is being consumed each day. That's this. And then, of course, we wanted our answer in teaspoons. So we ended with that conversion there and just kind of all combined together. So I really like this example. There's a lot kind of to it, and it really requires just a really careful eye and not getting overwhelmed by all of the numbers there. Use your common sense. Use all of your tools at your disposal to kind of see this piece of information is important. How are these two things going to go together? All of those things are going to be important to kind of think about when you get into more complicated problems and complicated scenarios. But yeah, so those are just some of the examples that you'll see with dimensional analysis. And obviously, it's used in a lot of context. A lot of times, just like whenever you're playing around with units, dimensional analysis is really what's going to be useful there. But yeah, so that is it for this video, and we'll have one final video just talking about word problems and studies and all of that in general. So look forward to that.